Alright, in some of the previous videos we looked at something called the critical section problem, which talks about how every process has something known as its own critical section, which is where those instructions or those parts of the process lie which are going to make changes to the data, where some data is being updated or deleted or written. We also saw how if two processes are going to be executing their critical sections at the same time, it is possible that it will end up in something called a race condition. So to avoid this, we saw that at any given point of time, at most one process should be allowed to execute its critical section. This was the critical section problem, for which we looked at something called the Peterson solution. We saw that it works well when you have only two processes involved, but when you have more than two processes, the Peterson solution fails to be of help. So we came up with something called mutex locks. Now we will look at one more solution to the same critical section problem. This one is called semaphores. So a semaphore is an integer variable. Again, in your mutex locks, we had this concept of a lock, which is in some sense a binary entity, locked or unlocked, 0 or 1 kind of a thing. Similarly, here we have this concept of a semaphore, which is also an integer variable, which can again be controlled by two operations, wait and signal. So if you remember from your mutex solution, again there were two functions, I think acquire and release, and those were the functions through which you could access this lock, acquire it, then work on your process, release it, and so on and so forth. Similarly, your semaphore again is an integer variable. Again, it can be accessed by means of two functions, which we shall call wait and signal. So the wait operation was termed from the Dutch word proberen, which means to test, and signal came from verhogen, which means to increment, which is just a bit of trivia. Let's not go too much there. So we will look at the definition of wait and signal shortly. But first of all, let us assume S is the semaphore or the integer variable. So I said semaphore is an integer variable, right? So here let us call that variable S. So what is this S initialized with and what does it represent? We'll look at that first. Then we'll come back to wait and signal very quickly. So what is this S? So before getting into that, there are two types of semaphores, counting semaphore and binary semaphore. So binary, as the name suggests, means your integer variable, your semaphore variable S can only take the values 0 and 1, which works similarly to a mutex lock. So it's either locked or unlocked, taken or available. So binary semaphore is almost the same as a mutex lock, which you are already familiar with. So we shall not be going into that direction again. We will focus in this discussion more on counting semaphore. So counting semaphore is an integer variable whose value can range over an unrestricted domain. It can be any integer, positive, negative or 0. So we will now see what exactly this stands for. So if you can see here, the semaphore is initialized to the number of resources available. This is what I meant when I said let's look at what the value of this integer variable stands for. So what do we mean by number of resources? It could be any computational resource which the processes are competing for. So I'll give you an example. Let's say there are 3 or 4 processes, all of which want to access your printer, the printer connected to your system or the printer which is available, and you have only one printer. So there are 4 processes, all of them want to print their own document or whatever. They cannot all send their documents to the printer at the same time and expect the printer to give out 4 pages at the same instance, right? So there is some competition between processes for accessing a resource. The resource in this case happens to be a printer. So there has to be some way in which one process acquires the printer, the other processes are notified, or there is some way of them coming to know that the printer is currently occupied. They wait, and once the first process has finished its task, the next one goes, and so on. So it's the same thing with any computational resource. It could be hardware resource, it could be a processor. Like in your scheduling context, multiple processes might be allocated to the same processor. They might be waiting for that. It could be some file, some location in the memory they want to access. It could be any kind of resource which the process needs in order to function, if there is a finite number of such resources, which is going to be the case in a computer, you only have so many locations in the memory, you only have so many cores in your CPU and so on and so forth. So when multiple processes are likely to need the same resource or the same type of resource, what we do is we use a semaphore to ensure there is no clash over there. So the semaphore is initialized to the number of resources available. So in this case, let us say you have 2 printers, then your S initially is set as S equals to 2. Now every process that wishes to use a resource performs a wait operation, thereby decrementing the count. Let's go back to how our wait function was defined here. Wait. So while S less than equal to 0, do nothing, busy wait, I'll explain. And then S minus minus. So ignore the while part for now, I'll come back to it in a minute. So if the while condition is false, meaning if your semaphore value is a positive integer, then the wait function asks you to decrement it by 1. What does that mean? So let's say we have 2 printers, the printer for example being the resource in question here. My S will be initialized to 2. So when some process calls the wait function, it obviously checks this condition S less than equal to 0, not true, so it skips that and comes to this part, S minus minus. So the 2 is decremented and set to 1. Now what does this mean? We had 2, but one of those resources has been taken up by some process. So when another process, let's say P2 comes, it will see that S is equal to 1. Again it will decrement it and S becomes a 0. So now there are 2 printers, both have been taken by one process each, and every time a process takes a resource, it is decrementing the number of available resources by 1 to indicate that I have taken up one instance of this resource. Makes sense, right? Perfectly straightforward. Now when a third process P3 comes, you see that S is equal to 0, so this condition is true, so it has to wait. Do nothing or busy wait means you want to be doing something, but because of the absence of resources or for some reason you're not doing it, you're waiting for something to be freed up. So that process is waiting, which is why we call it a busy wait. And once someone else has done with the printer, once someone else releases the printer, your S value will again be a positive integer, then this P3 can go and claim it. So that is the wait function. So this is similar to acquiring a lock in your mutex. So if the lock was false, or if the lock is held, you're supposed to do a busy wait, and once the lock is available, you set it to false, you acquire it. That is what your mutex lock or acquire function said, right? So this is analogous to that, except that your lock there is a binary thing, so only one process can have a lock at a time. Here, because this is a counting semaphore, the range is not restricted. Multiple processes can take up multiple instances of the same resource. Now, so we know how a resource is taken up. How is it released? For that, we have the signal function. So signal function, straightforward. Once you have done it, once you're done with using the resource, you increment the number by 1, meaning one more instance is now free to take up requests. So process P1 came, there were 2 printers, it took up 1, so it said it decremented the value of S from 2, it became 1. Now let's say process P1 has finished, so that printer is also free now, right? So it will increment the 1 and put it back as 2. So that is how your semaphores work.